Alright, I'm going to talk about E, Euler's number. Where did it come from? What's its origin? Well, it goes along with pi, golden ratio, and under root of 2. But the bad thing about E is it has nothing to do with geometry. You cannot describe it with any shape. It cannot be done that way. Like our famous pi 3.14 is defined as a circle's circumference and its diameter, and when you take this ratio it comes out to be 3.14, and it doesn't matter whether your circle is this small or that big. You can pick any circle as you please, and when you measure this circumference and diameter and when you divide this and you get 3.14, it always turns out to be this constant for any circle. You could also take a right angle triangle. This length is 1 and this length is also 1. Then this length is under root of 2, which is 1.414. And so these constants have geometrical interpretations. But E is different. E is spatial. It is about growth. It is about decays. It is about how fast something is growing. It's about that. Let me take you back in 17th century when it was first encountered, and it was Jacob Bernoulli who was solving the problem of compound interest. So you want to earn interest on your money in the bank. The original problem was, imagine that you have one coin in your bank and your bank happens to be so nice to you, they offer you 100% of interest for 1 year. So what happens after 1 year? You get 2. So you earn this one as your interest, and that's your original one that you put in. So after 1 year, you get 2. What if I tell you I can offer you 50% of interest for 6 months? Now, is it better? Is it better for your money? Let's try that. So after 6 months, you get as the interest, what's the 50% of 1? Well, that's half. And you get back your original money, that's your interest you have earned. So it is 1.5. And you do it again for 6 months for 50% of interest. What is the 50% of 1.5? Well, it is 0.75. And you get your original money back, which is now 1.5. So this becomes 2.25. So it's better. It's better. It's better for your money. And now you are getting greedy. You are getting greedy and you want to make a lot of money. And you ask me if I could offer you 25% of interest for 3 months. What happens now? Well, after 3 months, what is the 25% of 1? Well, it's 1/4. That's your interest you have earned, and that's your original money. You get now 1.25. And you do it again for 3 months. And now the interest you get is 0.3125. And your 1.25. What is it? Well, forget about it. You have to do it again, then you get something. Then you have to do it again, you get something. I don't want to do it this way. Things are getting messier. I'm lazy. I want to have a better approach. So now follow me closely. 1.5 can be written as 1.5, right? Look here. And what is 0.75? Well, it was the 50% of 1.5. It was half of 1.5. It was half of 1.5. And you can show that it is really 1 plus half to the 2. It shouldn't take you more than 15 seconds to show that, really. So what's really happening there is, this is the interest you have earned, 1.5 after 6 months, and you have to do it again for 6 months. So you do it twice in a year. That's why you see a 2 there. And the same argument can be used here. So that's the interest you have earned after 3 months, 1 plus 1 over 4, and you have to do it 4 times. So what happens after 1 year is you earn 1 plus quarter to the power 4, right? So what is it? It is 2.44. So it is getting better. So it will keep on getting better if your interests are frequent. Now, what if you do it for every month? So 1 plus 1/12, that's your interest you are going to earn, and you actually have to do it 12 times, right? So what is it? It is 2.61, I guess. Let me check. Yes, it is that. Now, what if you do it for weeks? You want to earn a lot of money, right? So 1 plus 1 over 52 to the power 52, it becomes 2.69. Now you are really greedy now. You want to do it for every day. You want to earn money every day. So 1 plus 1 over 365, and you do it for 1 year for 365, it becomes 2.71. So we are getting closer. It will become better and better if you do it for hours, for minutes, for seconds, for every moment. What if you do it for continuously? You want to earn money every moment. So let's do that. I hope you could see the pattern. It was really 1 plus 1 over n to the power n. And what I mean by doing it continuously, that you let your n to approach infinity. And then this becomes 2.71881, and it keeps on going forever and ever. And that's our E. It's about growth. Your money was growing for all the time. It is 2.71, and it keeps on going forever. Now, Euler used a different formula. He came up with 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 factorial, and it keeps on going forever. And if you do that, you will get E. Exactly. And he also showed that E is irrational. Now, I want to talk about e to the x. I want to talk about its derivative. E to the x, the function only calculus could have created. So, y is e to the x. And I want to know, if I take a function and I take the derivative, you get your function back. So derivative of a function is the function itself. So I want to find a function. Of course, you know it's going to do that. But I want to do it. Anyway, it's a differential equation, so I need a starting point. I need an initial condition, and I can have it. If I put x equals 0, you get y equals 1. Actually, I could have a 10 here, then I will have to multiply it with 10. I don't want to do that. I want to have 1 as my starting point. So let's do it. Y dy dx. So where do I start? Well, I start with my starting point, which is 1. Now these two has to be the same. They are same now. But 1 is not the derivative of that function. So I will have to add something here, and it is x. Do the derivative and you will get 1, right? But they are supposed to be the same. So I will have to add x again, right? but it is not the gradient of that function. I will have to add something here. What should I add? What if I add x to the 2? When I take the derivative of that, I get 2 downstairs here, so I will get 2 here, but I do not want 2. So I will have to multiply it with a fraction, which is half, right? And now take the derivative of that function. 2 will come out and 2 will eat this 2. So you get x, right? But these two have to be the same. So I will have to add 2 half x squared. But this is not the gradient of that function. So you see, I will have to keep on doing that. I will never going to catch up with this one. So what's the next term that I will have to add? So let me guess, what if I add x to the 3? When I take the derivative of that, I get 2 here, then I get 3. But I do not want 3 here, so I will have to divide it by 3. But I want half here, so I will have to divide it with 2, and I will show right. Take the derivative of that function, you get half x squared. But I have to do it, I have to add it, right? Now they are same. So I will have to keep on doing that. And so what is going to be the next term? Well, it's going to be x to the 4 with a fraction 1 over 24. So you will have to keep on doing that forever and ever. Forever and ever. So what if I do it for n times? So x to the n. So what is a fraction? I will have to multiply here so that I get my function. Well, it is all about the pattern. This is 0 factorial here, this is 1 factorial, this is 2 factorial, and this is 3 factorials, 3 times 2 times 1, and this is 4 factorial, then you will have 5 factorial. So I will have to multiply it with n factorial, which is n times n minus 1, and you will have to keep on doing that until you get 1. So what's the derivative of that function? Well, it is x to the n minus 1 over n minus 1. Keep on doing that until you get 1. But I have to make them the same. So I will have to add x to the n over n factorial. And you have to keep on doing that. Keep on doing that. Now you are going to suspect it. You may think this series is going to blow up because you have infinite number of terms. Well, not quite. Yes, of course, x is growing fast, but n factorial is growing even faster, way faster than x to the n, actually. And so what you are doing when you are moving in this direction, when you are adding more and more term, you are actually adding smaller and smaller and smaller number. So your series is really safe. It's not going to blow up. So I have just found you a function and its derivative, and they are both the same. So I want to see what if I set x as 1. What will happen? So you get 1, 1, then you get again 1, then you get 1 over 2, which is 2 factorial actually, then you get 3 factorials, then you get 1 over 4 factorial, then you get 1 over 5 factorial, which is 120, and you have to keep on doing that. And if you put this in your calculator, you will get e, and you could show that it is really the summation of 1 over n factorial, and it goes from 0 to infinity. Now I want to graph e to the x, and then I want to show you what does it have to do with this series? Let me graph that first. So it is e to the x squared, x cubed, x to the 4, x to the 5, x to the n. So the graph for e to the x, put x equals 0 right here, you get 1. So at 0 you get 1. Put x equals 1 right here, you get e somewhere here. It is 2.71. Put here minus 1, you get 1 over e, which is 1 over 2.71, which is really somewhere here, 0.3, let me check that, 6. And you do it for each point, you get somewhere here, new point. If you do it for this point, you get something here. And these all points will fall on this curve, and that's e to the x. So that's your graph. But what does it have to do with this series? How could this series possibly represent e to the x? Let me show you that how. So it was your e to the x, right? If you plot just 1, forget about all the terms, your 1 is right here, so it will go like that, right? A constant line. But now let's try it. 1 plus x. Well, x wants to go through the origin as a straight line, but when you add 1, it will go like so. And what if we try 3 terms? 1, straight line, and the parabola. Now you are going to see something is going to change. This plot, this graph is going to be like this. What if you do 4 terms? It becomes even better. It goes like so. What if you do for 5 terms? It becomes even better. It becomes almost better. It goes like so. What if you do for all the terms? It will go through e to the x. This series becomes e to the x. So that's how this series represents e to the x. So I want to show you, by the way, y is e to the x and dy dx is also e to the x. It's a phoenix rising again from its own ashes. Now I want to show you some remarkable things for e to the x. I think I don't need it anymore. Again, I am going to draw you the graph for e to the x. It goes like this. E to the x and x. At point x, the height of this graph is e to the x. If x is 1, the height is 2.71. But the derivative of e to the x, its gradient, is also e to the x. Also e to the x. So at point 1, your gradient is also 2.71. And there's one more thing. At 1 and all the way to infinity, this area is also 2.71. And so this is really a special function. It's a beautiful function actually. When you go from height to gradients, you have to do derivative. But when you want to go back, you will have to do integral e to the x of x, and you do it from minus infinity to e, and then you get 2.71, and that's area actually that you see here. So it's really a remarkable function. No one can touch it actually. It's really, no one can even come closer being as beautiful as this. So really great function in physics, in mathematics. Now I want to compare e to the x with other exponential functions. I want to compare e to the x with 2 to the x and 3 to the x. I will make graphs again, and I'm going to draw all of these graphs on the same plot. Even I am going to graph their derivatives on the same graph actually. So let me start with 2 to the x. Well, it's not a faster growing function, so it will grow something like so, right? 3 to the x wants to grow faster. You might expect it to go something like so, and they all will intersect at 1, right? Put 1 here, no, sorry, put 0 here, 0 here, you get 1. So it's like that. And you have somewhere in between, you have e to the x, right? Now you may feel, maybe you may try your intuition that maybe the derivative of 2 to the x is also 2 to the x, or maybe the derivative for 3 to the x is also 3 to the x. It's a feeling just, but you want to check it, you want to try it, and I will do it fundamentally. I will start with 2 to the x, the derivative of 2 to the x. I will start fundamentally. It is 2 to the x plus dx minus 2 to the x over dx, and you do it limit as dx approaches 0. Now you could write it as 2 to the dx, right? There's nothing wrong about that. So your 2x is common, it comes out of the limit, so you could write it like so. So it becomes really, you get 1 here, and your 2 to the x comes out, and the limit dx approaches 0. Alright, so let's approach 0. Put dx as 0 with 7 zeros. I hope they are 7, I'm not counting. But if you put that here and here, this limit will become 0.68. It becomes a constant. So what you're getting here is the derivative for 2 to the x is really not 2 to the x, but it has some constant with it. And then you have 2 to the x. So it's not 2 to the x, but it is proportional to itself, and the proportionality constant is 0.68. And you could do it for the 3 to the x. So let me change everything to 3, and if you do this limit again, when you approach dx to this, and you will now get a new constant which is 1.08. Let me check that. If, oh, it is 98. Let me check one more. Oh, this is really 93. So let me change it over. So here, so the derivative for 3 to the x is really not the function itself, but it has some constant, and it has a different constant now, and now 3 to the x. So this has a constant which is smaller than 1, right? And it has 1 which is larger than 1. So if I could plot its derivative on the same blackboard, on the same graph, it should go for 2 to the x, it would go like this. So it is below 2 to the x. And if you plot this on the same graph, the derivative, it goes like so. It is above this. So what I mean is, at this point, the slope's value is here. And at this point, the slope's value, this slope's value is right here. So this slope is below and this is above, and if you keep on coming closer and closer, there comes a line when it becomes the derivative of itself, and we know that line. It is e to the x, and its gradient is also e to the x, right? And you could show that. Go to your calculator. When you change it to e, you will see that you get this limit becomes 1, exactly 1. So you do not have a proportionality constant. Well, actually you have, it's 1. So this is what it is about. Now there's one more thing that I want to address, and it is, they do not write 2 to the x as 2 to the x. They do not write 2 to the x as 2 to the x in most books, in actually everywhere. Instead, they want to write 2 to the x in terms of e. Actually, they want to write everything in terms of e to the x. So 2 can also be written as e to the logarithm of 2. There's nothing wrong, nothing magic about that. You are just asking what should be the power of e so that you get 2 here. Let me tell you the answer. So 2.71, what should you raise it to so that you get 2? Well, you have to raise it to 0.693, and then you get 2. So this is and this is are the same. So if you take the gradient of this, I hope you know that if you have e to the cx, the derivative of that is c times e to the cx. So the gradient for this is ln of 2 e to the ln of 2 again times x. Oh my goodness, I forget to give it a x. Sorry for that. So if you take now the derivative of that, it becomes that. I actually forget to give them x. So this is 2 to the x, but I want to have them the same, so I will have to multiply it with ln of 2. So you can write 2 to the x as e to the some constant x. And what they do it now, if you could want to plot it, so you no longer call it 2 to the x. Instead, you call it ln of 2. Oh, excuse me. You call it e to the ln of 2 to the x, right? And if you had something else like a to the x, so you call a to the x as e to the some constant x, where a should be, oh sorry, c should be ln of a, right? The same argument. So they do not want to write 2 to the x as 2 to the x. They do everything in terms of e, in terms of 2.71, and it goes on forever.